You're about to embark on an amazing journey. But before you do that, let's make sure you have a basic understanding of what science is and what scientists do. So first of all, the basic idea of science as inquiry or scientific inquiry, to look at the words should give you a clue of what it means. Inquire means to ask a question. And that's where science has its basis. It tries to understand and explain phenomena that you observe in the natural world. Scientific inquiry goes back to the days of the ancient Greeks. Aristotle was one of the first people to talk about deductive versus inductive reasoning and scientific methods, things you've probably heard of somewhere. But he basically wanted to distinguish between what he called approximate reasoning, that sounds good, versus exact reasoning, saying this is why it happens in a step-by-step process. We break it down into 7 I can statements, and you can see those here. What scientific inquiry gets at is that we base information, we base processes on data, observable data that can be repeatedly obtained through experimentation and then is published or shared with other scientists who could, if they so chose, repeat your experiment and get the same results, get the same data. And there you can see that. So what should you be able to do then? If you're a scientist, there's 5 skills here, 5 things that you should definitely be able to do if you're doing science as inquiry. In all science classes, set out with the goal of you being able to do these things. And we'll look at each of these a little more in depth. So let's start with the first one. First of all, engage in scientifically oriented questions. Observations start with questions. If you don't have a question, you really can't do science. It's not a collection of facts, it's a process. And it is an explanation of how the natural world works. And so let's identify 2 basic types of questions. That is existence questions and causal questions. Existence questions ask the why. So little Timmy comes to mom and says, "Mommy, why are we here?" Well, that's a great question, and mom may answer that question based on her value system. We're here to help others, we're here to be good, we're here to make a lot of money, whatever it is. Whereas causal questions ask the how. Little Timmy might ask Mommy, "Mommy, how did I get here?" Mommy will probably say, "Go ask Daddy." I don't want to explain that to you, you're a little too young. The point is, there's why versus how questions, existence versus causal questions. So because some of these leave the realm of science, there are times that science cannot answer existence questions. Perhaps it can, perhaps they can shed some light on it, but the point is, if you want to think and act like a scientist, which needs to be one of your goals, you need to probably transition a lot of why questions into how questions. If that can help you answer why, great. The idea is, this is science, let's phrase our questions in ways that can be tested. And then let's give priority to evidence in responding to these questions. Simple terms, we observe, we gather data, and then we use that data to make conclusions. Those conclusions should be based on data that's repeatedly obtained, validated by other scientists, that they use it over and over again. I'll quote there on the bottom, explanations of how the natural world changes based on myths, personal beliefs, religious values, mystical inspiration, superstition, or authority. Those things are great, and many of us need those things. They're personally useful, it says. They're socially relevant. But in the end, many of those explanations are not scientific. They are not scientifically asked. They're more the why-type questions. And they are not based in evidence. The third thing is to formulate explanations from the evidence that we just talked about. There it is. Scientific explanations are consistent with available evidence. If, after conducting multiple experiments, or even 2 or 3 experiments, you find data that conflicts, all those ideas, all those explanations become open to criticism and are revised. There are many scientific ideas, big ideas, theories that have been out there for hundreds and hundreds of years that are still being criticized, still being revised. Some of them even changed as we get better technology and are able to set up better experiments. But those explanations are based in evidence, not necessarily what we want to happen or expect to happen. Many times it's not what we expect to happen. The fourth one, and I think this is probably as straightforward as any of them, connect explanations to scientific knowledge. Take your evidence, use that repeated supported data, and connect it. Explain how this supports what you're hypothesizing, how it maybe doesn't support what you're hypothesizing. The fifth one, the last one, is communicate and justify explanations. This is sometimes the hardest, especially for a high school student. You now have to take what you've done, take what you've seen, take the phenomena that you observed or observe someone else observing, and write it down, put it into words, type it out. Do so in a way that any other scientist could come along and do what you did, and hopefully they get the same results. Once again, to go back to what we just talked about, if they don't get the same results, it's open to criticism and open to revision. It can be changed. And this is what scientists do. Sometimes, maybe it's better to ask what scientists don't do. One thing that we hear a lot in everyday language is, I have a theory. You know, you may have a theory about how the Cubs could win the World Series if they just make a couple moves. This is not a scientific theory, it's just ideas. Ideas don't need any basis, they just need to be a gut feeling. In science, that is not what a theory is. And one thing that can drive science teachers crazy is when someone hears a theory and says, well, it's just a theory. There's no such thing as just a theory. If it's a theory, it's a well-supported, well-thought-out answer. And so scientists don't base things on just a theory. When they base them on a theory, it's well-supported, well-documented, repeatedly experimented, and come out the same results every time. Because keep in mind, they are open to criticism and revision. Another thing is that scientists base evidence on what they observe, not on necessarily what they want to observe or being paid to observe. Many times we don't understand how money can have a role in inaccurate scientific information, but there are many controversial topics out there. Global warming, genetically modified organisms, designer babies, evidence for evolution, that people have a vested interest in. And so they do experiments based on what they want to happen. And many times phenomena may work out one time out of 100. That's not science, that's one time out of 100. If it can be refuted and revised, that's what scientists do. So just keep in mind, at all times, approach science as a process. Use it as a way to gather evidence and to increase our understanding of the natural world. It's up to you to be a great scientist, and so good luck with that.